All right, so what we're going to do now is look at a simple circuit like what we had from last week's lab. So now we have our voltage source, our resistor, and our diode, but now it's an LED. It's a light emitting diode. We have our LED, light emitting diode, and we used a red one in that lab. So the reason that we have a resistor in series with this LED is so that it can limit the current. So we have a current limiting resistor. So that's the purpose of this resistor in this circuit. So there are sometimes, if you apply too much of a current to a diode or to an LED, you can have the diode actually burn out. So some of the diodes in the lab have like a little burnt spot, and you can see that they've actually been burnt out. You can even do that with normal diodes. So there's also a diode that I have somewhere hanging around as an example. You can see the packaging actually looks burnt because it had so much current going through it, it got so hot that the component is now burned out. So we don't want to do that, obviously. We want to make sure that whatever component we have hooked up to a circuit is operating within its safe parameters. So we need to limit current, and that's what our resistor does. And how it limits that is with the value of the resistor. So we can figure out what an appropriate resistor value is to get a particular current value. So let's say that we had a 100 ohm resistor. Let's see what current we're going to get there. So we'll say that we have I equals Vs minus dk over R. That's our general formula. We'll say that this is a red LED, so we should have a drop of about 2 volts for a red LED. And since we have a 12-volt supply, that means we're going to have 12 volts minus 2 volts divided by 100 ohms. So we're going to get a very high current. This is going to be 10 volts divided by 100 ohms, or we could say 0.1 kiloohms. So we're going to get an answer that is 100 milliamps. So that's too high. That's going to be a current that's not going to be safe for that diode. So let's say that we have instead a different resistor value. Let's say that we have a 2k ohm resistor. So let's see what we're going to get then for a current. We're going to have the same voltage drop because it's still a red LED. So we're going to have 12 volts minus 2 volts gives us 10 volts. And we're going to divide that this time by 2 kiloohms. And that's going to give us 5 milliamps. Okay, and that's actually going to be too low. So we're probably not going to have this LED light up at all if we just have 5 milliamps going through that circuit. And where are we getting these ideas from? Well, this is coming from a data sheet. So this is how I know if a current value is too high or too low for a particular component. So there's actually a link to a red LED data sheet that is in my lecture notes. You can pull that up. It's also on Eagle. But I just took a screen capture from the data sheet itself so that we could look at it here. And in the data sheet, there are a couple important things. So we have forward current, an absolute maximum rating in milliamps, 20 milliamps, so we don't want to exceed that. We don't want to exceed 30 milliamps for a peak current, so it can briefly get up to 30 milliamps but in general, we don't want to have more than 20. And there is this suggested using current, which is important, and that is 16 to 18 milliamps. So if we have about 17 milliamps, the LED will be bright and it will be in a safe range, so it won't have too much current going through it. We also have a forward voltage of 2.2 volts. So for a red LED, we have generally about 1.8 to 2.2 volts. So that's why I've been saying somewhere around 2 volts for a red LED. This one just happens to be a little bit on the higher end, so it's a 2.2 volt LED, red LED. Okay, so that's our information on the red LED from the status sheet. And that's how I know that 100 milliamps is way too high and 5 milliamps is way too low for our LED. So what we need to do is figure out an appropriate resistor value to give us a safe current value. We know what the voltage is. VD is 2.2 volts, and we know what the current should be, and that should be about 17 milliamps. And our safe range is 16 to 18 milliamps. Okay, so I'm going to see if I can just get rid of this stuff right here. And we're going to redo our calculations. So what we were using for a formula to get those different current values is our I equals Vs minus Vd over R. In this case, we know what Vd is, we know what I is, and we're interested in finding a resistor value that'll give us an appropriate current. So we need to solve this for R. To get the resistance, and all you're going to do there, you can just switch the positions of I and R. So you can go through the algebra for it, or you can just remember that shortcut. So R is equal to Vs minus Vd over I. Okay. So what we're going to do now is figure out a range of safe resistances because we have a range of safe current values. So we'll start off with that one. That'll be our first resistance value, and we'll start off using this 16 milliamps. So we've got Vs minus Vd, and that is over our first value, which is our lower current value. So we've got 12 volts minus 2.2 volts. That's divided by 16 milliamps. And I'm just going to round to 2 volts because this is for the safe current region. So, or it's a suggested operating region. So we can be a little bit safe above and a little bit below that. So assuming that this is just 2 volts, that would give us 625 ohms. All right, so that's one of our resistance values. And then for R2, we're going to use our other current value, Vs minus Vd over I. And this is now our higher current value. So we're going to have 10 volts over 18 milliamps. And what that would give us is going to be a lower resistance value, and that is 556 ohms. Okay, so this is our min and our max. Okay, so what do we do with these? We don't have exact resistor values. We have certain resistor values that are manufactured, and so we need to find a standard resistor value that falls within this range. Okay, so within that range, we actually have a couple options. There is a 560 ohm resistor or a 620 ohm resistor. And you could use either of those and you would get a current value that's going to be within that safe range of 16 to 18 milliamps. Okay, so that's how you can find an appropriate resistor to limit the current to within safe values for your diode.